Thank you very much, and thank you to the organizers. I'm very, very pleased to be here. Today I'm going to talk about some non-generic isomonodromy deformations, and we'll present a joint work with Giordano Cotti and Dubrovin. Dubrovin sadly passed away a few months ago, and this work was done before that. The problem I'm going to talk about is the following. So suppose we have this linear system of differential equations. This system has a Fuchsian singularity in 0, regular singularity, and an irregular singularity at infinity. And this matrix lambda is a diagonal matrix with eigenvalues u1 and un. So I will explain you why I'm considering this system, but the important point, just to do the analysis of this system, is that this u varies in a polydisk, which I call D. I will specify this polydisk later. So what we are interested in is the case when some eigenvalues merge inside the polydisk. So inside this polydisk D, there will be what I call a coalescence locus, namely a locus where eigenvalues coalesce. So, as I will explain later, the theory of isomonodromy deformations requires, I mean the standard one, requires that the eigenvalues are distinct. So the purpose is to extend this theory to the non-admissible case, namely when eigenvalues merge. So why shall we consider this system, which in a sense is a particular kind? There are so many differential systems. Why shall we consider this one? Why is it important? So actually this system appears in many applications. The first one, first of all, we can say that it is related to Fuchsian systems. So Fuchsian systems are studied for several reasons. We have just heard a talk before about hypergeometric equations. And actually, by a Laplace transform, you can relate solutions of this system to solutions of a Fuchsian system. I will not enter into details because I'm not interested in this now. Another reason is that in case the system is three-dimensional, then this system, well, I didn't say in the beginning, actually we are interested in the case when the dependence of our system on the parameters u is isomonodromic. So in the case the dimension is 3, the system is one of a representation, an isomonodromic representation for the Painleve 6 equation that we have seen this morning. There are usually the representation for the Painleve 6 equation is given by a Fuchsian system, which is maybe one of the reasons people say Painleve 6 is the easiest one. But there is another representation which is given by a 3×3 irregular system. And if we call t the variable of the equation, the independent variable, this is related to our eigenvalues in this way. So coalescence of eigenvalues corresponds to t going to 0, 1, and infinity, which, as you remember from this morning, these are the fixed singularities of the Painleve equation. The main motivation to study the system for us is actually that it is related to Frobenius manifolds. So what are Frobenius manifolds? I'm not going to explain, of course, this is a very long story, but let me say that essentially Frobenius manifolds were introduced by Boris Dubrovin in order to give a geometric description of the WDVV equation of associativity in topological field theory. And these manifolds are manifolds with the property that if you take the tangent space at each point, this is an algebra, actually Frobenius algebra. So there is a multiplication. You can multiply vectors. And this multiplication is commutative, associative. There is a unit, and so on. And there is a flat metric, which in a sense is compatible with multiplication. And the condition of associativity of this multiplication, and together with the fact that the metric on the manifold is flat, allows you to express the structure constant of multiplications as third derivatives of a function f. This is exactly the condition that the algebra is associative, and this condition is called WDVV equations. So I'm not going to talk today about Frobenius manifolds, but this is just to give a motivation. And moreover, Frobenius manifolds seem to be a universal, well, universal may be a big word, but we'll say a universal object in mathematics. Namely, they have many applications. They appear in several applications. They are related to singularity theory. So if you take the space of versal deformations of simple singularities, here is just an example. Deformations means A1 and A0 and AN minus 1 are parameters which deform the simple singularity x to the n plus 1. So these spaces have a structure of the Frobenius manifold. Another example is orbit spaces. If you take, for example, Cn, and you take the quotient, so the orbit space, with respect to a Coxeter group, you get a Frobenius manifold. You can take more generalizations of this when W is an extended affine Coxeter group, or even other generalizations when W becomes a Jacobi group, and so on. Then Frobenius manifolds actually are a natural setting for to study integrable PDEs, because actually you can construct PDEs of a hydrodynamic type using the geometric structure of the manifold. This theory goes back to Dubrovin and Novikov. And one example which is very much studied today is the case of quantum cohomology. Namely, you take a variety x and the cohomology with the usual cup product, and then you do a deformation of this product. The deformation is a product which depends on deformation parameters t, and the multiplication is actually generated by the third derivatives of this function. And this function is important because actually is the generating function of some invariants, which are Gromov-Witten invariants, namely some numbers which properly count intersection, number of curves or cycles which intersect in proper ways in the manifold in the variety X. So there are several applications. So why? So what is our system? What has our system to do with this? Actually, there is this important characterization of Frobenius manifolds. That let's say that a manifold is Frobenius if and only if you can find a flat connection on this manifold, which depends on a parameter z. So it's a family of flat connection depending on z. And the condition of being Frobenius is, let's say, essentially equivalent to the fact that this family of connections are flat for every z. In case the multiplication in the tangent spaces has no nilpotence, so we say that this algebra is semi-simple, at least on an open-dense subset of the manifold, then we can choose on the manifold a set of coordinates, which I call u1 and un, which are called canonical. And where these are different, actually, so this is an important condition, the condition that the connection is flat is exactly our system plus the condition that this system is isomonodromic. I will not explain how this happens. It's a long story, but this is just to motivate why we want to study this system, which is isomonodromic. There is an important consequence of this characterization, namely the monodromy data of this system, which are locally constant because the system is isomonodromic. So they locally do not depend on you. So they locally do not depend on where you are in the manifold. So they become, let's say, a way to parameterize locally the manifold. So in a way which is not really precise, but let me say in this way anyway, that charts of the manifold can be parameterized by monodromy data. And actually, there is a way to reconstruct the local structure of the manifold just using this monodromy data in an explicit way, actually. So if you have the monodromy data, you actually can construct the system used by some Riemann-Hilbert problem, and then from the system you can reconstruct the manifold. And actually, you can also do an analytic continuation of the manifold. Given a set of monodromy data on a chart, there is a simple action of a braid group which can give you the data on another chart. So it's enough to know the data on a chart, so it's enough to know the system on a chart, and you can do the analytic continuation of the Frobenius manifold structure. So it's important to know the monodromy data of the Frobenius manifold if we want to know the global structure of the manifold. And so if we want to apply this knowledge to what for example, quantum cohomology, so enumerative geometry and so on. So this is a motivation why we want to study this system. So let me go back to this system, isomonodromic system. So first of all, suppose that the matrix U has distinct eigenvalues. Here we are in the case of admissible admissible deformations, and the theory of isomonodromic deformation in this case, well, is very well explained in, for example, in the paper by Jimbo Mio and Ueno. And we know that if you want to compute the monodromy data of the starting system, it's enough to compute the data of the system in one point, because they are locally constant. For example, if we take this polydisk where the eigenvalues are distinct, and so also the center of the polydisk has different coordinates, so just take your system in the center of the polydisk and compute the monodromy data. Now, let's consider again our system, but in the case when we have a coalescence point. So the center of the polydisk, which I call UC, C stands for coalescence. So the center is characterized by the fact that some eigenvalues are equal. Not all, maybe some. So this is a case where the deformation is non-admissible. And by the way, in dimension greater than 1, if there is a coalescence point in the center, there is a full coalescence locus inside the polydisk. So we ask the same question. Can we compute the data of the original system if we fix the system at the coalescence point? So actually, the problem it's hard, because when the eigenvalues of the leading matrix coalesce, we lose several good analytic properties of solutions, and also monodromy data. Suppose you can define monodromy data of the system at the coalescence points. In general, they are not very easily related to the points when you go out, when you move away from the coalescence locus. So let me just give an example. This is not an isomonodromic system, but it's a very easy, simple example. So suppose we have this system, and here we have a coalescence locus actually in C, in the complex plane, which is U equal to 0. Now, if you take a solution of the system, a fundamental matrix solution, so with a non-vanishing determinant, you have this structure of this. This is a canonical structure, actually. So you have some exponential parts, some powers, which are actually 1 and 2 here. You see 1 and 2. And then y hat has an asymptotic representation. So when z goes to infinity inside some sector, you have this asymptotic representation. Now, u equal to 0 is a coalescence point. And as you see, this is a pole in the asymptotic expansion. So there is a problem in the asymptotic expansion. Moreover, you can write this solution explicitly. You need this exponential integral. So it's the formula. Maybe you can. It's not important to look at all details, but anyway, this exponential integral here appears, and you may know that when the argument of of this exponential integral goes to 0, we have a logarithmic log branch. So when u goes to 0, we have a branching around u equal to 0. So this coalescence locus, which now is just 1 point, is a branching locus for solutions. And even when you take the limit when u goes to 0 of our solution, actually here there is no limit, but there is a solution for this system when u is equal to 0. Actually, there is a whole family of solutions depending on parameters, but the limit is not this one. So you see that even in this very simple example, there are problems. But anyway, we would like to extend the isomonodromy deformation theory in this case. Of course, there is some, let's say, necessary condition we need to impose. First of all, we assume that A of u is holomorphic in our polydisk where there is coalescence. So in this case, why are we interested in this extension? Well, first of all, in case of Painleve transcendence, so when the system is three-dimensional, there are cases when A of u is holomorphic at coalescence points. This is the case when we have Painleve transcendence which remain holomorphic at one of the fixed singularities of the equation. In this case, actually the solutions are have a Taylor expansion at the singularity. We can study them using, for example, Fuchsian systems. So there is not much to do. Well, there is not much new to say about this case, but anyway, our 3x3 system may give you a computational approach which is different in this case. So now I will develop a theory in case of coalition points, and you will see that if you apply our results in this case, the computations are easier than those you can do using Fuchsian systems. Another, so the main motivation is this: in case of Frobenius manifolds, if we have a Frobenius manifold such that the multiplication remain semi-simple at coalescence points, so when some canonical coordinates of the manifold merge, so in this case, the corresponding matrix A of u you can prove is holomorphic at the coalescence points. And we would like to extend the isomonodromy deformation theory in this case because there are several interesting cases when we know the system, so A of u, only at coalescence points. So I try to repeat. We are interested in the monodromy data of the Frobenius manifold because they are local parameters. They are necessary if you want to study the structure, local and global structure of the manifold. But in cases we are interested in, we know our system only at coalescence points. So if you want to apply an isomonodromy deformation, we have to extend the isomonodromy deformation theory to this point. So for example, this happens for quantum homologies of Grassmannians. And this was actually our original motivation. So let me first of all review the standard isomonodromy deformation theory to show you what are the differences when we allow presence of coalescence points. So this is the case Jimbo Mi was studying in a sense. I will present it in a slightly different way, which it's more suitable to the presentation. So I will present it in the following way. So what does it mean for me that the system is isomonodromic? It means that there is a Frobenius integral Pfaffian system, which is this one, where omega, this differential form, is a form in variables z, u1, and un. So the z part is actually the part which is governed by our differential system. And then there is another remaining part, which is this one, with holomorphic coefficients in C times our polydisk. So I remember, I recall that this polydisk has no coalescence points. So if we derive a specific structure of these omega j's, we can guarantee that some monodromy data are constant. Actually, I have not defined the data yet, but I will define them. So first of all, the fact that these coefficients are holomorphic, it allows you immediately to conclude that there exists an holomorphic solution, which depends holomorphically on the parameters u, and has a singularity in z equal to 0. So in this R stands for the universal cover of C minus 0. And the fact that Y satisfies the Pfaffian system immediately implies that the monodromy around 0 is constant. In this, I will call this kind of solution a weakly isomonodromic deformation, isomonodromic solution. Weakly means that the only thing which is constant, well, essentially is this matrix M. There are other monodromy data which I will introduce later which are not constant. So there is a characterization which is quite old of this kind of solutions. You can always choose solutions which are in Level form. Namely, there is some invertible matrix here. There is a convergent Taylor series with holomorphic coefficients. And then there is this logarithmic part, z to the d, which is, d is a matrix of integers, and z to the L. L is another matrix, which is the log of the monodromy. An important point is that actually, you see the condition that this matrix satisfies the Pfaffian system implies that these exponents are constant. And actually, also the eigenvalues of the matrix A are constant. These two objects, which give me the D and L, which give me the monodromy M, because they are actually essentially the log, these are for me actually the monodromy data I'm interested in. There is also another set of monodromy data which are important. So recall that our system has an irregular singularity at infinity. So if you want to describe solutions at infinity, you have to study, well, you can give just asymptotic representation of solutions in some sectors. And there is a Stokes phenomenon, namely change of asymptotics when you go out a sector. In order to do this, to study this, I need to introduce the notion of Stokes rays. So you take lambda of u, which is the matrix of our eigenvalues, and then you associate to them rays, which are given by these equations. Maybe it's better to look at the picture. So these rays are in the universal cover of C minus 0, but if you project this cover, you will see these rays on C. So if, for example, if you take the lambda of u0, there are some rays, these black rays. Then if you take another values of u, so take lambda of u, so these rays will be different, but there will be rays. Here in blue, I represent a line, an arbitrary line, which has the property that it does not contain the black Stokes rays, namely the rays associated to the center of the polydisk. So I call this an unmissable line. This is somehow conventional, but it's necessary if you want to define a Stokes phenomenon. So once this setting is done, now we can introduce sectors. So maybe I go back to one slide. So let me call tau the direction of this blue line. So I can construct sectors by extending half planes like this. So maybe it's better to look at the picture. So I take, for example, this half plane below. Take the Stokes rays which come before and after the blue line, and then extend and consider the sector which extends the half plane up to the nearest Stokes rays. So this is a sector, then you can do it for another sector, and then you can continue on the universal cover. So we can find an infinite series of sectors, which I call SR. R is an integer. And since there is no coalescence in our polydisk, when u varies, rays move, but they never cross the blue line. So if we take the intersection of when u varies in the polydisk of this of a sector SRU, you get a sector which is smaller, of course, but the opening angle of this sector is still greater than pi, more than a half plane. So this is very important because it allows us to define the Stokes phenomenon. So first of all, you can solve our system formally. This is a formal solution. The structure is an exponential part with the matrix lambda. There is a log part where B is a matrix with entries given by the diagonal part of A, and F is a series at infinity. This is a formal one which does not converge. The coefficients are holomorphic in U. And then result due to Shibuya tells you that in any sector introduced before, you have an actual solution with the same structure, and this Y is holomorphic in the sector with asymptotic representation given by this series. So it is essential that the Stokes rays in the previous slide do not cross the blue line when U varies. Otherwise, this proposition does not hold. So if everything works well, if we do not have any coalescence point, we can define these asymptotics in fixed sectors. And then we can define what are called Stokes matrices, so connection matrices which connect solutions in different sectors. And here I also introduce a matrix which connects our solutions with asymptotic representation to the solution I introduced before here. Okay. By the way, just a remark. The condition that, integrability condition of our Pfaffian system implies immediately that B here is constant. So actually, the diagonal entries of A do not depend on U. Okay, now, what is I give a definition, actually, a little bit strange, maybe. I call the deformation U strongly isomonodromic if all the matrices with asymptotic representation also satisfy the Pfaffian system. So it's not difficult to prove that a necessary and sufficient condition for this is that the Stokes matrices, and so here is CR, so C0 are constant in the polydisk. It's enough to consider S0, Stokes matrix S0, S1, and C0 because there are formulae, simple formula which relate S0 to S2R and S1 to S2R plus 1 and CR to C0. So it's just enough to take S0, S1, and C0. Another small remark is that the monodromy at 0, as you may remember, this gamma is not here, is the exponential of the matrix L, which I have introduced in previous slides, and the monodromy at 0 of a matrix, of a fundamental matrix YR is this one. So monodromy is determined finally only by this data, which I call essential monodromy data. So for me, monodromy data are not these monodromy matrices, but are these data. So Stokes matrices, exponent B, IL, C0, and D. D actually does not appear in the monodromy, but if you want to know the eigenvalues of the matrix A in our system, then D is necessary. So as a conclusion, in admissible isomonodromy deformations, so when we do not have any coalescence, we can well define essential monodromy data which are valid for every U inside the polydisk. And the most important point is that we can define the Stokes phenomenon without any ambiguity. Okay, maybe this remark. If you look at the paper by Jimbo and Miwa, AU is required to be non-resonant, but everything I've said holds also when A of U is resonant, so it's not so important. Now let's go now to the non-admissible case. So we suppose, again, there is a coalescence. So the center of the polydisk has some merging coordinates. So there is a full coalescence locus inside the polydisk. And again, I can define Stokes rays for lambda u and Stokes rays for lambda evaluated in the center of the polydisk. So this case, since there is a coalescence, first thing you may notice is that if you take, these are the black rays, are rays associated with the center. There is a certain number of rays in the projection of the universal cover on the complex plane. When u goes away from coalescence points, more rays appear, of course, because this is definition. So the red, these are rays when u is away from the coalescence locus. So actually what happens is that a black ray splits into 3 rays. For example, these 2 rays and this ray here. Maybe next slide is even more explicit. So suppose, for example, you have this kind of coalescence. So label coordinate I and coordinate j are equal in the center of the polydisk, but they are different from the coordinate k. So this is the ray associated with I and k, or j and k, which is the same. So when you move away from the coalescence locus, you have 3 rays which appear. So the ray associated with j and k, the one associated with I and k, and let's say the one associated with I and j, which is this. And now if u varies inside the polydisk, if the polydisk is small, these 2 rays here, they move, but not too much actually. There is a problem with this ray. This ray crosses the admissible line. The admissible line with respect to the center of the polydisk. So no matter how the polydisk is small, from the very definition of Stokes rays, here you see, you have ui minus uk. So here when you do a loop around, so here it was I and j coalescing. When you do a loop around ui and uj, this ray will make a full turn of 2 pi. So this means that inside the polydisk there are points which belong to a subset which I call x tau. Tau is the direction of this blue line, which I call crossing locus. So it's exactly the locus of points which are associated with this crossing. So when the value of u is such that the red line is on the blue line, I say that u belongs to this crossing locus. So you can prove the following, that if you take the polydisk minus the coalescence locus and the crossing locus, the polydisk is divided into topological cells. So simply connected domains which are homomorphic to a ball, or to Cn, sorry, to R2n. This is a very, let's say, schematic picture. So this is a polydisk. Of course, I cannot draw the polydisk, but in n complex dimensions, there is a coalescence locus which passes through the center, and then there is this yellow or orange, I don't know, locus, which is the crossing locus. So when you, for example, you are here and you go downstairs, you go through the crossing locus. This corresponds to the fact that a Stokes ray is crossing the admissible line. Now, what can we do now in order to work with this? Of course, we cannot define a Stokes phenomenon properly because we have this crossing of Stokes rays. So one thing we can do is to start with, by the way, I didn't say, each of these cells, I will call them tau cells because they depend on the choice of the admissible direction. So let's suppose, so the only thing we can do is, let's first of all look at one cell. So in this case, we have no coalescence inside one cell. So here we can apply the standard isomonodromy deformation theory. So I call U0 the center of in a smaller polydisk inside a cell. So here I can apply the standard isomonodromy deformation. So I have a Paffian system. Maybe I didn't say what is the actual form of omega, but maybe it's not so important now. So maybe, but anyway, it's F1 was the first matrix in the formal expansion at infinity, and EK is a matrix with zeros every way, except for the point in position KK. Anyway, so here we can apply the standard deformation. We can define, well-define Stokes matrices and all the other monodromy data, which are constant in this polydisk, in the cell. Now it's really important to look at this. So if you do the formal computation of F, which is a very easy computation, you can find the structure of omega k. So omega k is singular at the coalescence locus. There are poles. And so problems arise, which are the following. Since we have a Paffian system with poles, first of all, we may have branching locus for solutions of we may have branching at the coalescence points for fundamental matrix solutions. The second thing is that if you compute explicitly the coefficients of the formal expansion, this is explicit computation you can do. They have poles at the coalescence points, and what I have already said, it's not possible to define properly a Stokes phenomenon in the whole polydisk because of crossing of Stokes rays. Now, if you look at this again at this omega, you may see here that at least there is one case when this omega is holomorphic at the coalescence locus, namely when the matrix, there is no one, sorry, it's a mistake. When the matrix A, the component ij of the matrix A vanishes when you reach the coalescence locus. So suppose you reach coalescence locus, and at that point ui and uj merge. So our matrix A, which is not 0 in general, but suppose that it vanishes there. So in that case, the problem number one, namely problem with branching, is immediately solved because we have a Paffian system with holomorphic coefficients. So this is an easy problem to solve. We can extend solutions to the universal cover of C minus 0 across the whole polydisk. The second problem can be solved also. You can prove that all the coefficients of the formal expansion are holomorphic. This is done by iterations. Actually, you have using your Paffian system, you can prove that there is this kind of recursive relation. So if you prove that F1, which is this, is holomorphic, which is the case with this under this assumption, then by recursion you can prove that all the coefficients Fk are holomorphic. But the last problem is the hardest one. So how to define the Stokes phenomenon, because we have this crossing of Stokes rays. So this can be done, and this is the hardest part of the analysis. You can do this analysis also in the non-isomonodromic case. So you can consider a general system like this with not just one A over Z, but sorry, here there is Z to the power J. Sorry, there is another misprint. Z to the power J. So there is a full expansion at infinity, which is uniformly convergent in the polydisk. So if you assume, which is actually the case in the isomonodromic case, if you assume that all the FKs of the formal solution are holomorphic in the polydisk, and if you assume that the solution with asymptotic representation have an analytic continuation for you in the whole polydisk, then even if the system is not isomonodromic, so there is no Paffian system behind, you can prove the following. First of all, you can prove that the asymptotics is actually well defined for every u in the polydisk in sectors which are sectors which are even wider than those I have presented before. So in wide sectors of angle, central opening angle which is greater than pi. And the reason why this happens, and which is actually the main ingredient of the proof of this property, is that you can prove that there is this vanishing property of Stokes matrices. So with under the only assumption, maybe I go back, sorry if I go back, with the only this assumption here, you can prove that the Stokes matrices, which for non-isomonodromic systems depend on U, they actually have vanishing entries corresponding to labels I and J for which two coordinates are equal at the center of the polydisk. And then the second property, which is also very important, if you take the system evaluated at the center of the polydisk and you take a formal solution of the system, actually you can prove that there is a formal solution which is exactly equal to a formal solution of the original system evaluated in the center. And this formal solution has asymptotic expansion. Sorry, to this formal solution there are some actual solutions corresponding, and they are actually the actual solution of the original system evaluated in the coalescence point. And the Stokes matrices are just the limit. The Stokes matrices of the system evaluated in the coalescence point are just the limit of the Stokes matrices away from the coalescence point. So I will not prove this because it requires a lot of work, and this work is required precisely because the system is not isomonodromic. So you have to really analyze what happens to fundamental matrix solutions when you move inside the polydisk. But now that we have this theorem, we can apply the theorem to the isomonodromic case. Maybe there is another point maybe I should remark. Like actually, formal solutions of the system evaluated at the center, which I call Y with the ring upstairs, actually there is a whole family of formal solutions. There is only one of them which correspond to the formal solution away from the coalescence point evaluated at the coalescence point. But in the case, the entries, diagonal entries of the matrix A, or the matrix A1, sorry, in this A1, they do not differ by integers. There is only one choice, is this one. So now let us apply this to the isomonodromic case. So in the isomonodromic case, the assumptions of theorem 1 are satisfied. So we can directly apply this theorem. So maybe, so you consider our system. First of all, you can conclude that the essential monodromy data, which are these pink ones, S0, S1, L, C0, and D, are well defined in the whole polydisk. And moreover, you can compute them just by computing the monodromy data, which are the blue ones with the dot upstairs, of the system at the coalescence point. So you take the fundamental solution with the asymptotic representation corresponding to a formal solution here. And then you compute the Stokes matrices and so on. And then you take any Levelt form of the system here. You compute the exponents. And then you are sure that these are exactly the monodromy data for the system away from the polydisk. So we have also a computational, if you like, a computational way to compute the data here. Just restrict to this system, which in a sense is simpler. So maybe we can skip this corollary, which is like more or less what I've already said. So if you want to compute the monodromy data of this, just compute the monodromy data of this. And the important point is that the computation of the monodromy data of the system at the coalescence point may be feasible explicitly because of this condition. So this system here at the coalescence point is simpler because some entries vanish, And in some cases, you may even compute explicit solutions using special functions. So that's why in the title of the talk I wrote some computational, I don't remember even the title, anyway, computational method, some computational approach to isomonodromy deformation, because actually this is the reason. And another point, so I come back to the application I had in mind. Now, if you want to compute the monodromy data in the whole polydisk, it's just enough to know A at the center. And this is the case in applications, for example, in quantum cohomology. Maybe I should mention that there is also, just for completeness, there is a converse of the theorem 2 here. The converse is the following. So suppose now that we have a strongly isomonodromic deformation in a polydisk contained in a cell of the UC. So you remember the picture with the polydisk divided, and then there is a smaller polydisk inside the cell. So suppose the deformation is isomonodromic here, and suppose that there are entries of the Stokes matrices which are vanishing with labels corresponding to the coalescence point. Then in this case, you can prove, using a Riemann-Hilbert approach, that solutions to the isomonodromic solution to our system actually have no branching at the coalescence locus. They are meromorphic functions now, not holomorphic in nu, but at least they are single valued. I call this a weak converse because, well, maybe the word weak is, well, in some sense it's weaker. So I remember Boris Dubrovin did not agree with this, but in a sense, I think this is a weaker theorem. Maybe just some literature. So you may ask if this kind of results are already in the literature. Actually, we were not able to find them. Several people studied case of coalescence of singularities. Here there is a list. But these studies, actually, they were maybe concerned with leading matrices which are in Jordan blocks, and they were concerned with the change of behavior of solutions, I mean, relation of solutions at the coalescence point and away from the coalescence point, change of asymptotics, change of Gevrey order in the asymptotic expansion. But we were not able to find any result of where the leading matrix remains diagonal at the coalescence point, and when you can actually prove that solutions can be well defined in the whole polydisk in a holomorphic way, and the data remain constant in the whole polydisk. So maybe some applications. One is to Painleve equations. I just take this simple example. This is a Painleve 6 equation with just one parameter. This morning, this parameter was called alpha. This is a different representation, which is essentially due to Boris Dubrovin, because this is actually related to three-dimensional Frobenius manifolds, and mu is a parameter which appears in Frobenius manifolds. Now, the isomonodromy deformation equations for our differential system, which in terms of the matrix A are this one, they are equivalent to the Painleve equation. And here you may observe that we have a coalescence. For example, this is the parameter in the equation, and these are the eigenvalues of our matrix. So for example, take t going to 0. This means that u2 coalesces to u1. You can rescale the variables in the system and reduce the differential system to this one where only t appears. And so we have a coalescence of two eigenvalues when t goes to 0. Okay. So we may consider, this is a toy example if you like. one solution of this Painleve equation. This is an algebraic solution. So it is given in this this way. This is a uniformization of this equation, of this solution. So it's a zero genus curve. And if you expand this solution at t equal to 0, it may have several branches. Some are multi-valued, some are not. So I pick up the holomorphic branch, which is a Taylor expansion. The entries of the matrix A can be expressed explicitly as algebraic functions of y. So I don't write the formula, but the formula give you this expansion, Taylor expansion. This is a convergent. These are convergent expansions. And so you see when t goes to 0, which is a 1 and 2 coalesce, 1 and 2, you have that A12 goes to 0. So we are in the, this satisfies the assumptions of our result. And actually, you can now take the system at 0. This is the matrix A0. So here, just this one and this one. And now, just compute the monodromy data of this system. So this will be the monodromy data associated to this branch of the Painleve equation. Since this system is very simple, you can solve it explicitly in terms of Bessel functions. And so everything can be done, and you can compute Stokes matrices and so on. So this was just a toy example because these results are already known. They have been known for 20 years or 20 years or more, but this just to tell you that everything works. If you take another branch of this algebraic solution, you see here what are the A's. So here A's actually diverge. So we are not in the case we are considering. The assumptions of our theorem are not satisfied. So the other example is Frobenius manifolds. So first of all, you can prove that if you have a Frobenius manifold which remains semi-simple at the coalescence points of canonical coordinates, then A of u is holomorphic. And also you can prove that the entries of the A goes to 0 corresponding to the coalescence. So all these assumptions of our theorem are satisfied in this in case of Frobenius manifold. So as I have already said several times during this talk, we can now just rely on the knowledge of A in the coalescence point. And this is the case, for example, in quantum cohomology of Grassmannians. In this case, one can prove, as Giordano Cotti did, that for almost all values of k and n, and I will not specify what almost means, but so almost all the times, we have a coalescence phenomenon, and the structure of this quantum cohomology, which is a Frobenius manifold, is known only at coalescence point. So if you want to know the monodromy data of this Frobenius manifold, we only have this, and so we need the theorems I've explained before. And so, for example, this is a simple example. If you consider this Grassmannian, this is our lambda view. We have coalescence, two coalescence points. You can verify explicitly that the entries are 0. We have everything explicitly. We have our system explicitly, and we can solve the system explicitly in terms of generalized hypergeometric functions. So this is the Stokes matrix. We also have this central connection matrix. Sorry, the matrix C0, here there is a 0. And everything can be computed. So you may ask why this is important. So one reason is, as I already explained before, the main reason is that these data are just local. Then you can extend them using an action of the braid group. And so in principle, by a Riemann-Hilbert problem, you can reconstruct the structure of the whole manifold. So you start from one point, you know the monodromy data, and then you can do the analytic continuation of the Frobenius manifold. We used this result in order to verify and refine some conjectures. Actually, this was our original motivation, Dubrovin original motivation, which is the following. So I say it again. monodromy data are important to do the analytic continuation of the Frobenius manifold. In general, it's a problem to compute monodromy data, but Dubrovin conjectured that you can compute monodromy data in algebraic terms. So, namely, the monodromy data of the Frobenius manifold, they are actually equal, up to some admissible transformations, to some algebraic quantities, which I'm not going to explain, that you can associate with the so-called exceptional collections in the right category of covariant sheaves of the variety you are considering. So I'm not going to explain this part, but just to tell you that you have two sides of the problem. You have the analytic problem, so our system, you should compute monodromy data. So we were lucky in that case. In some cases, you can actually do the computations as we did. But in general, if you have a system of differential equations, it's very hard to compute the monodromy data. The conjecture tells you, don't worry, goes to the algebraic side. Algebraic side. There are some algebraic objects which are associated to your manifold. Compute algebraic quantities which algebraic geometers can compute. These are the data of your manifold. So the first point was, is this conjecture true? So we verified this and actually refined this conjecture using the result we had. So in case of Grassmannians, the results I have just presented justify the computations of monodromy data starting from a coalescence point. This justifies the fact that these are actually the data which are locally valid, and then you can extend them by analytic continuation. And using this data, we could prove actually that the conjectures are true. So maybe now I'm out of time. I will skip the last slide, which is actually the conjecture in more details. And I thank you for the attention.
Thank you, Davide.
Welcome.
Any questions? Yes, please.
I was wondering, did you, with these systems, Stokes phenomena is, at least in systems of differential equation, well described by using Borel transform.
So this is a good question. Yeah, so we did not do that because we reached the result. But in principle, you can do this by Borel transform. And you can also do this by more or less the same, passing to the Fuchsian system. In this case, the Fuchsian system has coalescing singularities. And using some result by Bollybrook, which says that anyway, even if you have coalescence, the singularities remain regular. So I believe, I'm sure, that you can prove the same. We did not do that anyway.
Anyone else with a question? Okay, if not, I suggest we thank Davide.
Thank you.